What if the universe isn't doing what our best theories say it should? Precise measurements of cosmic expansion don't agree. Dark energy looks like it's changing, and new studies even argue expansion is slowing right now. Tonight on VibeVerse, we dive into why the universe's expansion doesn't make sense and what it could mean for the fate of everything. For a quarter century, cosmology's standard model looked unshakable, a universe made mostly of dark matter and dark energy, expanding faster and faster due to a mysterious repulsive force. That picture came from Type Ia supernova, standard candles, baryon acoustic oscillations, and the cosmic microwave background. But now, the strongest datasets disagree on the basic number that describes the current expansion rate, the Hubble constant. This split, called the Hubble tension, and by some, the Hubble crisis, refuses to go away. Meanwhile, hints of evolving dark energy and fresh challenges to supernova assumptions suggest our map of cosmic history may be missing key landmarks. If the expansion is actually slowing today, as bold 2025 analyses claim, then the next chapter of the universe could be radically different from the infinite acceleration once imagined. Let's unpack the paradoxes, the measurements, and the possibilities. Fact 1. One universe, two Hubble constants. Hubble constant HO is the present-day expansion rate of the universe, measured in kilometers per second per megaparsec. Early universe inferences, mainly via the cosmic microwave background fitted with the standard CDM model, give a lower HO. Late universe distance ladders, primarily using supernova and Cepheids, return a higher HO. Both methods are highly precise, and their disagreement has become more statistically significant over time. Two answers can't both describe the same cosmos, unless there's new physics between early and late epochs, or systematic errors lurking in the data. The crisis deepens because independent late-time methods like strong lensing, time delays, and tip of the red giant branch distances broadly support the higher HO, while the early time fits remain internally consistent and elegant. Either the distance ladder is biased in subtle ways, or the early universe model assumptions are incomplete, or both. That is why it's called a crisis. Precision and coherence are pulling in different directions. Fact 2. The CDM comfort and its limits. CDM lambda cold dark matter is the minimal model, a cosmological constant for dark energy with W equals -1 constant density per volume, cold dark matter to seed structure, and general relativity governing spacetime. It fits the cosmic microwave background beautifully, and explains large-scale structure with remarkable success. But CDM assumes dark energy doesn't evolve, and that standard candles are well understood after empirical corrections. When late-time data disagree with early-time CDM inferences, either the candles aren't perfectly standardizable across cosmic history, or is not a true constant, or gravity behaves differently than assumed. The model's simplicity is both its genius and its Achilles heel. Fact 3. The supernova pillar under Ray examination. Type Ia supernova built the acceleration claim in the 1990s, earning a Nobel Prize. But a 2025 analysis argues that supernova brightness depends on host population age. Older environments yield subtly different luminosity profiles than younger ones. If not fully corrected, that age bias can mimic or amplify signs of acceleration. This doesn't mean no acceleration ever by default, but it does mean that the confidence with which we assert its current magnitude, or even its presence today, may have been overstated. If supernova standardization drifts with population properties, the late-time HO and acceleration inferences must be recalibrated with stricter demographic controls. Fact 4. A shocking claim. Slowing now, not speeding. A bold 2025 result argues that, after correcting for host age biases, present-day data shows no evidence for ongoing acceleration. In fact, the universe may have already slipped into decelerated expansion. If true, dark energy would not be constant, it would evolve, and may be weakening faster than expected. This claim stands in tension with other probes that still see evidence for acceleration. The path forward is clear: assemble much larger, cleaner supernova samples with precise host age measurements, cross-check against lensing time delays and bow distances, and decisively test whether the slowdown now scenario survives. Fact 5. DESI and evolving dark energy spectroscopic instrument DESI and other large-scale surveys have hinted that dark energy's influence might be changing with time. In some combined fits, allowing dark energy to evolve improves consistency with certain datasets, but it can exacerbate the HO split when not handled carefully. If dark energy is not a pure cosmological constant, its equation of state W may be -1 only on average, drifting across epochs. Even small departures from W equals -1 can ripple through expansion history, altering distance redshift relations and growth of structure. Theories range from quintessence fields to early dark energy blips that tweak pre-recombination physics. Fact 6. Early dark energy and pre-recombination fixes. One promising idea injects a small, transient dose of dark energy in the early universe to reconcile CMB fits with the higher present-day HO. This early dark energy changes the sound horizon scale imprinted in the CMB and bow, nudging inferred parameters closer to late-time measurements. The catch: these models must be finely tuned to avoid spoiling the CMB's exquisite fits and the formation of structure. So far, none has become consensus, but they show how delicate adjustments to cosmic initial conditions might bridge the gap without overhauling gravity. Fact 7. Could gravity itself be different? Modified gravity theories FR gravity, scalar tensor models, massive gravity aim to reproduce early universe successes while changing late-time dynamics to fit acceleration or a higher HO. Some implement a screening mechanism. Gravity behaves like general relativity in dense environments, but deviates on cosmic scales. Observational reality check. Modified gravity must pass solar system tests, binary pulsar timing, gravitational wave speed constraints, and large structure growth. A consistent theory that fixes HO, preserves local tests, and matches growth data remains elusive, but the door is not closed. Fact 8. The juiced, too early galaxies. UNIACETH James Webb Space Telescope found surprisingly mature galaxies at very high redshift, hinting that structure formed faster than many models expected. If galaxies assembled earlier than anticipated, either star formation was more efficient, dust and stellar populations are tricking our inferences, or the cosmic timeline through HO or dark energy history needs adjustment. While this is not a settled crisis, it adds pressure. Multiple, independent tensions point to the late-time universe being under-modeled. If early galaxies were indeed so massive so soon, our assumptions about the growth rate of structure, feedback physics, or even expansion history could demand revision. Fact 9. If slowing now, what's next? If dark energy is fading and expansion is already decelerating, gravity could gradually regain dominance. The far future cosmic forecast would shift from eternal acceleration to a universe that slows, potentially levels off, or even turns around into contraction. The Big Crunch possibility revived in modern guise. This is not a prediction yet, just a logical endpoint of the slowdown claim. Future surveys will track the deceleration parameter, growth of structure, and distance ladders with unprecedented precision to see whether the trend points toward a calmer expansion or a cosmic U-turn. Conclusion: doesn't the universe's expansion make sense? Because our best rulers give different answers. Our simplest dark energy story may be too simple, and bold new work suggests the cosmos could already be decelerating. It's the frontier doing what frontiers do, forcing better questions, sharper tools, and deeper theories. Whether the fix is hidden bias, evolving dark energy, early universe tweaks, or new gravity, the next wave of data will decide if cosmology needs a tune-up or a rewrite. Until then, stay curious. When the universe disagrees with us, it's inviting us to learn its real language. TAFE, you want to follow up breaking down HO methods, evolving dark energy models, and how standard sirens can settle this? Hit like, drop expansion in the comments, and subscribe to VibeVerse. The cosmos is changing our minds in real time. Don't miss the next plot twist.